So to start off 6.2, 6.2 will be all about integrals involving u substitution. So the idea is when we dealt with derivatives, we had a lot of rules like the product rule, quotient rule, chain rule, and things of that nature. But when we have integrals, we have a lot of rules to reverse them. And the one that we're going to focus on that covers the majority of cases is u substitution. So to start off with, we're going to introduce a fact that says given any integral, the integral of f of x dx, this is equal to 1 over k times the integral of k times f of x dx, as long as k is some non-zero constant. Meaning, although it might not make sense why this is useful now, you can take any integral you want and multiply a constant inside of it, as long as you multiply the reciprocal of that constant to the outside. A quick proof of why that's true is if you were to pull this k outside using our typical rules, you'd end up with k times 1 over k on the outside, which is just 1. So you're multiplying by 1. You're not changing the problem. And again, this might not seem useful yet, but it will become useful as we get deeper and deeper into the section with u substitution. Alright, so from there, we're going to introduce another fact that says if y is equal to f of x, y is some function of x, then, then dy dx, the derivative of y with respect to x, is equal to f prime of x. So again, this is just standard derivative notation that we've been working on for quite a while now. But here's the really important step. If we were to put f prime of x over 1, we would then have two fractions equal to each other. And if we cross multiply these fractions, we would end up getting dy times 1, which is dy, equals f prime of x dx. Which means if you're given y is equal to f of x, then automatically you can say dy is equal to f prime of x dx. Now that might not seem very useful, but think about how this could be incorporated into an antiderivative or an integral. F prime of x is the integrand, what's plugged into the integral, and dx is always what's multiplied to your integrand inside of the integral. So we're saying we can rewrite what's inside of the integral, what we have here, as just another dy or du or dw. So we can change everything in the integral to something else using this rule. And again, this might not seem very useful yet, but as we go through these steps, you'll start to see where it comes into play. Okay, so continuing along with this, let's say we have the following question. The integral of 2x times e to the x squared plus 1 dx. How do we take the antiderivative of this term? If you notice, we have multiplication of two functions going on, 2x and e to the x squared plus 1. That should automatically be a red flag that something's off here. We don't know how to take an antiderivative with that. And then on top of that, we have e to the x squared. We only know the antiderivative of e to the x. So what's going to happen with that x squared there? We need to find a way to rewrite this into a more manageable problem that we know how to deal with. Something like the integral of e to the x dx. If we could rewrite the problem to look like this, then we could take the antiderivative. So we have to come up with that method to rewrite it. So in comes u substitution. Now you may have heard about U substitution in a previous college algebra class. This is a form of it. So to start going through how it works, the first step in the process of U substitution says that we need to search the integral for a function you can integrate, meaning a complicated function, not something simple. So for instance, in that last problem we had, 2x e to the x squared plus 1, e to the x was the most complicated thing in that function. So we look through the problem, we notice e to the x, the function e to the x, and we know we're going to need to work around that. Once we know what that most complicated function is, we can go to the next step, which says we need to let u equal what is inside of that function, meaning what's being plugged into the function. Once we let u equal what's being plugged into the function, we have now performed our u substitution step. And from there, we can find the step we mentioned earlier, that dy equals f prime of x dx, but instead of dy, it's du. du equals f prime of x dx. And the reason we find this is we are changing the variable in the original problem to a u instead of an x. But in order to integrate, we will now need a du at the end of the integral instead of a dx. So this is where the substitution comes in. We substitute u and du in, leaving only u's instead of x's. And then once we do that, we can integrate because we'll have a problem that looks as simple as this. And after integrating, we can replace u with its original value, thus finding the original antiderivative. Alright, so let's go ahead and give these a try. For the first problem, we have the integral of 2x e to the x squared plus 1 dx. So the problem that we started with earlier. So for this problem, we need to start by finding our value of u. We need to find the most complicated outer function and then what u is. So in this problem, the most complicated function, like we said earlier, was that e to the x. But what's being plugged into e to the x? The x squared plus 1. So we're going to let u equal x squared plus 1. And now that we have that, we find du. Remember, du is literally just the derivative of u all times a dx. It's as simple as that. Just take the derivative and then multiply it by a dx. So what's the derivative of x squared? Well, that's 2x. What's the derivative of 1? 0. So we get 2x times dx. And with this u and this du, we can substitute them in, hence the u substitution. We can substitute them in and replace our variable x with u's. So we get the integral of 2x e to the x squared plus 1 dx. I'm going to substitute it one step at a time. As you get further along in these problems, you'll be able to do it all in one step. But just to make it make more sense, we have the integral of 2x e to the x squared plus 1, we said was u. So we get e to the u dx. And now from here, notice we have a 2x and a dx technically being multiplied together. They might not be attached to each other, but we could always rewrite this problem as e to the u times 2x dx. As when you're multiplying, you're allowed to change the order. And now 2x dx, we said earlier, is du. So we get the integral of e to the u du when we substitute du in for the 2x dx. And now hopefully you can quickly understand what the antiderivative of e to the u du is. That's a problem we've done quite a lot. The integral of e to the x is e to the x, so the integral of e to the u du is e to the u plus c. Always remember the plus c. And now that we have that, we can finish this by substituting our value of u back in to our final answer, because we started with x's, not u's. The u's were just the work to get to the final answer. So we have e to the u is x squared plus 1, so e to the x squared plus 1 plus c. And that is our antiderivative. You could do a quick check to see if this is accurate. If you took the derivative of this, you'd use the chain rule. Remember the derivative of e to any power? You take the derivative of your exponent and multiply it out front and keep everything else the same. So what's the derivative of x squared plus 1? It's 2x. So the derivative of all of this is 2x times e to the x squared plus 1, which is exactly what we started with. So we have done this correctly. Alright, from here, we're going to try one more together, and then I'll go ahead and have you all try the next one, and then we'll do that one together as well. So, starting this off, we are looking for a complicated function. Well, there isn't really anything complicated about this except the fact that it has a fraction. So remember, whenever you're dealing with a fraction, typically the denominator is going to be the most complicated thing. So whenever you're doing one of these u substitutions or an integral that you think might involve a u substitution, generally look to the bottom or the denominator to see if your u can be found from there. So we're going to let u equal the entire denominator, which is 4x plus 3, which means du must be the derivative of this times dx. So what's the derivative of 4x? 4. What's the derivative of plus 3? It's 0. So we get 4 dx. Alright, so let's start plugging this in. We have the integral of 1 over 4x plus 3. Well, we said 4x plus 3 is u, so we get 1 over u dx. And from here, if we were to put this dx over 1 and multiply these two fractions together, we would get the integral of 1 times dx is dx over 1 times u is u, which leaves us with the integral of dx over u. Well, we can't take the integral of dx over u because we need to have a du there. Remember, we said du is equal to 4 dx, but right now we only have 1 dx. So how can we get that to become a 4dx? Well, that involves the rule that we introduced at the beginning of today's section. If we multiply the inside of the integral by any constant, remember this is only true for constants, so I'm multiplying the inside of it by 4, and I'm allowed to do that as long as I multiply the outside by 1 over 4. And now that we have that, 4 dx is now in the top, which gives us 1/4 times the integral of 4 times 1 times dx is just du over u. And now try to think about what the integral of du over u is. It might not be very intuitive because it looks a little different than what we've talked about in the past, so I'll rewrite it. Du over u is the same thing as 1 over u du. And now hopefully you can see that the integral of 1 over u, meaning what did we take the derivative of to get 1 over u? We have 1/4 times the natural log of the absolute value of u. And again, always remember the plus c. And with this, we can now move on to the last step, which is to substitute u back into the problem. So we get 1/4 times the natural log of the absolute value of 4x plus 3 being plugged into u plus c. Alright, so remember it's always the same process here. We look for our complicated function. If we don't have one, it's generally going to be the denominator of our fraction or something in the denominator. We take that value and set it equal to u and find du. We plug u and du in for what we have, and we multiply by a constant along the way if need be. We can then take our antiderivative and then substitute our value of u back into the problem. Okay, with that, go ahead and take a moment to pause the video and try this problem on your own. Okay, so now trying this together, again, we don't have a complicated function, so odds are u is going to be the denominator, 5x minus 6, which means du is the derivative of this times dx. The derivative of 5x is just 5. The derivative of minus 6 is 0, so we get 5 dx. So going to this problem, if we were to move this dx to the numerator, or in other words, multiply by dx over 1, which would put the dx into the numerator, we'd get the integral of 2 dx over 5x minus 6. We don't need 2 dx though, we need 5 dx. So how can we get that? Well, we'll multiply by 5 over 2 on the inside of the problem. And when we multiply by 5 over 2 on the inside, we have to multiply by 2 over 5 on the outside, the reciprocal of what we multiply to the inside. And with that, we can now perform our u substitution. We have 2 over 5 times the integral of 5 halves times 2, I might as well write out this step to show what's going on, would give us 5 dx over 5x minus 6. So we have 2 over 5 times the integral of 5 dx is du. That's our u substitution for du. And then 5x minus 6 we said was u. So we have du over u. And now we can take the integral of that. We said in the previous problem, the integral of du over u is the natural log of the absolute value of u. So we get 2 over 5 times the natural log of the absolute value of u plus c. And finally, always remember, we need to plug u back in. Because we didn't start with u, we started with x. So we get 2/5 times the natural log of the absolute value of 5x minus 6 plus c. All right, so with that, we have one last case that I want to go through for u substitution in section 6.2. So in this case, again, we look at the problem for the most complicated function. Again, we have a fraction. So we're going to let u equal the denominator and see if it'll work out. So u equals x plus 2, which means du equals the derivative of x plus 2. Well, the derivative of x is 1, and the derivative of plus 2 is just 0, so we get 1 dx. So going through our u substitution, we have the integral of x over x plus 2 we said was u, and dx, well, we said 1 dx, or just dx, is du. So the integral of x over u du. It's tempting to want to start taking the antiderivative here because we have the du, but we can't as long as that x is in the problem. It has to be only u values. So we have to do a little trick here, looking back to the original u substitution we used. We said u is equal to x plus 2. Can you think of a way to get x alone from here? Well, if we subtract 2 from each side, we get x equals u minus 2. And now we can substitute that in for our x value, giving us the integral of x is now u minus 2 over u du. And although it might look like we're now in a problem that's just as complicated as what we started with, it actually turns out that this is much easier. In the original problem, we dealt with a fraction that couldn't be broken up because the addition was in the denominator. But in this fraction, we can break it up because the subtraction is in the numerator. Remember, as long as it's in the top, you can break it up. So this becomes the integral of u divided by u minus 2 divided by u. Remember, as long as the addition or subtraction is in the numerator, you can split it up into two separate fractions over the same denominator. And all of this is times du. So simplifying, we get the integral of u divided by u is just 1 minus 2 divided by u du. And we can now take our antiderivative. The antiderivative of 1 is just the variable that we're working with, u. It's tempting to say x, but remember our variable is now u. So we get u minus the antiderivative of 2 over u. Might not seem apparent right away, but think about if it were 1 over u. What's the antiderivative of 1 over u? It's the natural log of the absolute value of u. So what's the antiderivative of 2 over u? It's 2 times the natural log of the absolute value of u. And this is all plus c. And from here, we can plug our value of u into our final answer, which gives us u becomes x plus 2 minus 2 natural log of the absolute value of u again is x plus 2, all plus c. Whenever you're left with something like this, where you substituted in u and du, odds are you've either made an error, which you should go back and double check, or you need to look if you can use one of these tricks to solve for x and plug its value in to allow you to take your antiderivative using u.